Hi, today we will go through how to comply IEQ minimum air quality for LEED version 4. So this is for existing building and operation and maintenance. So I will go through some of the basics of fresh air or outdoor air requirement as well as LEED VRP calculator. So let's begin with this credit requirement. Of course, we understand this credit is about outdoor air, about fresh air, but the intent is to contribute to the comfort and well-being of the building occupants by establishing minimum standard for indoor air quality. So that's the intent. And if you look at the requirement, so in this case, there are two types of spaces. First of all, is we have to understand what is meant by mechanical ventilated spaces. So for LEED, when you say mechanical ventilated spaces, means that any area that use mechanical system to bring in or to bring out air. So this means air conditioning spaces as well. So the other space is a natural ventilated space. So first of all, it's very important to confirm the area and the type because it will affect the project information form as well as all the overall submission. It means all the AC space must have outdoor air, must have fresh air. So if the area is deemed to be natural ventilated, but there's a split aircon which without OA, if that area can meet the natural ventilation requirement, so declare that area as natural ventilation. We'll go through the natural ventilation requirement in a moment. So first of all, after determine the area as a mechanical ventilated or ventilated area, we also must determine the area whether it's occupied or not occupied. In LEED, when it says occupied space, means that it's an enclosed space intended for human activities. So exclude those spaces such as storeroom, equipment rooms, or those only occupied occasionally for a short period of time. So exclude those areas. So for example, equipment, machinery, storage, or sometimes you just go into that room to get some equipment out. All these are unoccupied space. So with that, we have to divide the area into four types of spaces. Air conditioning occupied space, air conditioning not occupied space, natural ventilated occupied space, natural ventilated not occupied space. So if we divide this into four areas, and then we have to tell LEED that all these spaces, how is the outdoor air served? Obviously, non-occupier space, you don't have to include the outdoor air. But for occupied space, either it's by air conditioning, outdoor air, or we meet the natural ventilation requirement. If we look into the requirement for the LEED for BOM, first of all, case 1 is say that system able to meet the required outdoor air rates. So the standard that LEED use is ASHRAE 62.1. We need to fill up the ASHRAE VRP or ventilation rate procedure form. I will show in a moment. We have to meet the minimum required in the section 4 to section 7. Next, if the system not able to meet, existing system not able to meet the outdoor airflow rate, LEED allows you to go for 5 liters per second or 10 cubic feet per minute of outdoor air per person. 5 liters per second per person. So if you're not able to meet, then you go for the case 2. But in order to comply to case 2, you have to submit an engineering assessment to tell LEED that the current system not able to meet. So the advice is to go for case 1 because case 2 LEED will question a lot. They will ask you this and that, ask you to prove this and that. So it's harder to justify for case 2. So if it's best case, go for case 1. First of all, let's look at our single zone. So in the calculator, there's a 3 type of space that you can input in. First is single zone. So if you look at the schematic over here, all the zone is only one zone, whether it's served by ASU or served by FCU. So let me show you in the whiteboard. So single zone means you have a ASU or FCU. So it doesn't matter ASU or FCU, as long as it's served by a zone. So you have a mixed air going in, and then you have a out air, and then you will have this air to circulate back again. Then you have a mixed air going into the space. In this case, if this is only one zone, so you can go for a single zone requirement. In this case, what's important is the O air. Okay, so the LEED doesn't care so much about the supply air. This one don't need to take account. So we just look at the OA into the zone. So either by this way or the other way will be direct going in. So let's say you have a space and you have FCU serving the space. So supply air and return air. And you have bringing an O air. So in this case, this is also considered as single zone. So whether the O air direct going in, treated or non-treated, whether it going into the FCU and supply to the person, is the same case. So this is a single zone requirement. Or sometimes you also have some spaces that you have multiple spaces. You have a primary ASU that's serving O air into all this area, PASU, which means PASU, primary ASU, only treat fresh air. It serve all the fresh air to all the area. This is also considered as single zone. You can put it as a single zone, also can put it as 100% fresh air. So we'll go through this in a while. Important thing is to know what is the amount of O air into each of the spaces. This is the important information. Let's look at the input for the fresh air calculator later. So let's go through this quickly on the calculator. First, you have a unit. Usually we use a SI unit. Next, in this case, we'll go for LEED V4. If you are designed to provide more than 30%, so this one you click yes. If not, you just click no. Usually, if you just want to meet this prerequisite, so usually we just click no. Next, this is where you input in the single zone system. So if you have a single zone system, you just click yes. So when you click yes, it will appear this single zone. So in single zone, it's rather simple. Just input your system name and your number. So in this case, you can just put in, let's say ASU 1 serving, let's say office space. Next, cooling, we serve cooling. Occupancy category, this is where you choose what type of occupancy you are. So in this case, we go for, let's say, office. What is the area? In this case, I chose SI, so it's in square meter, let's say 100 square meter. Am I using a default rate for zone populations? So this one LEED doesn't care so much about the default or non-default. In this case, if you want to go for default, it's fine. If your space, if you think that not enough fresh air because of click no, then you input what is the people inside that space. In this case, we go for yes, doesn't matter. And next is the exact value. So exact value, we can go back to the instruction, look at the exact value. Exact value, there's an explanation over here. Yep. First one will be ceiling supply of cool air. This is most of the case where you have cool air coming up from the ceiling supply. Ceiling supply of warm air and return. In Malaysia climate, there's no warm air, so we don't do heating, and actually skip all this. And the other one is usually the number is 1. The higher the better. The only one that they allow is 1.2, which is a floor supply of cool air and ceiling return. The low velocity displacement ventilations. This one is kind of rare. We don't have much of this kind of system. In this case, we go for CS, ceiling supply of cool air. So exact put 1. So in this case, the zone outdoor airflow, which is the OA requirement, is 43 liter per second for this single zone system. So you can put, if you can design more than that, you put 50. So in this case, it must be more than 43. All right, that's for single zone. So for single zone, you can just add on another system. So let's say you have 5 systems, you just add on another 5 systems, just input accordingly. So next system, we look at 100% outdoor air. So what does it mean by 100% outdoor air? So 100% outdoor air is those spaces. Let's say we have multiple spaces. So it's served by a ASHU. So in this case, this is PASU, primary ASHU. Air coming in and going into all this area, or it can be a single zone as well, but is fully served by PASU, which means it doesn't have FCU or ASU in here. So it doesn't have, which means it's primarily depend on the primary ASU. So primary ASU don't have circulation. So the function of primary ASU is just take in outdoor air, treat it, and then supply to the area. In this case, same as the single zone as well, the amount of OA is important. How much the OA going into the space. So how much OA going into space. So for, let's say, hospital, for example, ICU or operation theater is 100% fresh air. So in this case, we go for 100% fresh air calculator. So a slight difference between 100%. So if we go back to the VRP calculator, next we can, in a step 5, we can add in either multiple zone or 100% outdoor air system. In this case, you can add system and choose 100% outdoor air and just put your system name. Alright, so for example, in this case, I just input in some of the area, for example. So zone name, let's name any, what's your zone name, just name it. So in this case, let's say you have a kitchen cooking, 100% outdoor air. Same case again, what is the floor area? Are you using default value of zone population? What if you're using default, this will be automated calculated. So same case again, your exact usually is 1, you can put 1. And what is the zone outdoor air provided? So same case as a single zone as well, just that in this case, you will have an additional this area. So in this area, it will calculate the amount, the total amount that required. So total amount in this case, let's say I have two area. So what is the summation of these two? So this is the required. So required in this case is about 69.70. So 100% outdoor air, you have to comply 2 requirements. First is what is your zone outdoor air, your outdoor air provided in each of the space, as well as to meet what is the total. So in this case is 69, so either by 70 or above. So 2 requirements. One is the each zone and also the total one, where you have the ASU, PASU serving all this area. So for 100% fresh air, you have to meet the OA in depend on space, as well as what is the total going in. So you must meet all these requirements. So for example, some of the area where you have primary ASHRAE serving, but for some of the area, let's say you can't avoid FCU or split unit. So in this case, let's say this space you have FCU, this case you have some split unit connected outside, you have FCU where it provide a local cooling, air going in, going out. So you can actually just ignore all this. You can ignore all these things. So if you have a local cooling, all these things doesn't matter. You still use a 100% outdoor air calculator, input all the O air accordingly. For single system as well as 100% outdoor air system, LEED doesn't care so much about the supply air. So supply air will look into a multiple zone. So remember there's 3 zones: single zone, 100% OA zone, and also the multiple zone. So now we'll look into the multiple zone. And same, go to the instruction. You have add system and delete system. So you can add a multiple zone system. So multiple zone is a bit more data to key in. But what does it mean by multiple zone? Single zone, you have ASHRAE, FCU, serving one zone, then you have fresh air coming in, either going into the ASHRAE, directly going into the space, or you have 100% outdoor air, you have a primary ASHRAE serving all those areas, supplying dedicated O air into those spaces. But in multiple zone, is different. So you have one AHU serving all this area. So you have O air coming in, and then you have air going into all these spaces. In this case, I have 8 zones served by one AHU, and O air going into this AHU, which means the outdoor air is mixed with the return air. So return air going back to the AHU. So which means the O air supplied to the AHU and then get mixed up with the return air and put into the supply air and supply to each of the zone. Multiple zone is a bit more complicated. You need to know few of the number in order to input into the calculator. The first number, the total outdoor air into the area. The second number you need to know is your total supply air. Total supply air going into, let's say in this case, 8 zone. And the third thing you need to know is the amount of the supply air to all this zone. Let's say this is zone 1, zone 2, zone 3, zone 4, and so on. You need to know the total amount of supply air into each of the zone. Let's look into the calculator. All right, so in this calculator, so you can look into the multiple zone. So it's cooling, and this all zone are included in a VRP calculator because some case there will be a zone excluded, maybe because it's too small and whatnot. So in this case, my advice is to put everything yes all into the zone, or else you have to provide an explanation to LEED why these zones are excluded in the VRP calculator. Same thing, zone name. You can have occupancy category. So in this case, let's go for office as an example. Same thing again, your zone area. In this case, I just put 100 as an example. So am I using a default value for zone population? Okay, yes. So it will automatically calculate my people. And what is my exact? In this case is ceiling supply cool air 1.0. In this case, I have to input 2 number. Okay, my zone discharge airflow. So my zone discharge airflow means that my supply air into each of the zone. So let's say this is zone number 1, my office space. How much is my supply air going into that zone? Okay, let's put 50 liter per second. Sorry, too small. Let's say 200 liter per second. We have a primary and also secondary. Allow you to have a secondary recirculation. So secondary recirculations, this is more appear on those country that has this what we call heating recirculation. So there has this PFP box for heating purposes, which means you cool the air and then you reheat it, going back and coming back again. That is secondary recirculations. But in Malaysia or in cooling climate cases, there's no secondary heating or cooling. In this case, I supply 200 into my zone. So don't have secondary recirculation. So my primary airflow is same as my total supply air. In this case, it's 200. You put the zone primary airflow and the zone discharge airflow is the same. So it doesn't matter what is your ER is. This ER is your recirculation fraction if you have a recirculation. So if you want to know more about ER, you can go to instruction. So there's a quite extensive explanation on what is ER. ER is more like how do you recirculate your secondary zone. So in this case, doesn't matter, just put any number. Continue to put some other spaces. Let's say in this case, I just put the art classroom. Yes. This is for the purpose of this exercise. And okay, let's put one more. For example, let's put okay, lecture classroom, put about 150. Yes. So you can see the default is according to 62.1. So let's say in this case 1500 is 1. All right. So in this case, you don't have to worry much on what you input up here. Okay, compared to single zone as well as 100% zone. So single zone and 100% outdoor air zone. So you have to make sure that your supply outdoor air was enough for each of the single zone. So when we look at multiple zone system, there's an additional input down here. The first one will be system population. So what the system population means, let's say I have one zone 100 people, the other zone 50 people. But at the same given time, when it overlaps, it might only have 120 people. So in this case, I can input 120 people, which is less than what is the sum of all this zone population. Because if you look at all this zone population, if all add up is 142.5. Okay, I can input much less, 120, in case I know that at a given time, people will be much less than this. But just for simplified the input, we can put the same as this 142.50. And next one, system primary airflow. This is total supply air into all this zone. In this case, total supply air into all this zone is actually 2700. Some of this, but sometimes it can be less because a VAV system, which means this might be the maximum. For example, art classroom, this might be the maximum 1000 into that room in a VAV system. But in the total supply air, I can design lower. Again, just to simplify for all this, let's assuming we don't have VAV system or CAV system, is the sum of all this supply air into all this zone, which in this case is 2700. So we can actually just input in 2700. The next one is this. It asks which method from ASHRAE 62.1 being used to determine system ventilation efficiency. There's a two-way to determine the EV, and that's using table 6.3 or using appendix A. This one you can play around. Usually appendix A will be more better for us because the EV higher, the fresh air is lower. So you can just use appendix A. But sometimes in some of the case, table 6-3 actually give you lower fresh air. But this must be consistent for all the input, all the multi-zone input. If you choose appendix A, means all must be appendix A. In this case, our outdoor air required for this ASU is 901, which means the OA that we must supply for all these zones must be higher than 901. For example, it can be 1000. All right, that is for the multiple zone system. Let's recap again. There's a total 3 system. First is the single zone. Second will be 100% fresh air or OA. Third is multiple zone. For single zone, so any zone that have single and served by ASU or FCU, that you have OA going in and then serve this space. The important point is the OA volume. Second zone will be 100% fresh air, 100% OA. You have a ASU as well. In this case, primary ASU. Same thing as here as well, primary ASU. Primary ASU, the air coming in, and you can serve few of the spaces. Okay, which means for case 1 and case 2 is all the OA going into the space. By meaning going into space is can be direct into the ASU, FCU, or going into the space. This number is important, and this number is important as well. Third case is the multiple zone. So for multiple zone, you have OA going into the ASU. And from this ASU is supplied to all the zone. But at the same time, there will be return air back into this ASU, which means our OA will be mixed up with the return air and going into the space. In this case, this number is important, and supply air into each zone is important, and total supply air into all the zone is important for the input. That's it for the input for the VRP calculator. Okay, now let's go into natural ventilation. Okay, so for natural ventilated space, so the requirement in LEED is saying that we need to determine the minimum air opening and space configuration requirement using the natural ventilation procedure from ASHRAE 62.1. ASHRAE 62.1, actually there's a clause saying that the natural ventilation requirement. In order to confirm the air opening, we need to look at the space configuration. That's step number 1. Step number 2 is to check the natural ventilation effective strategy. So in this case, they are using a SIPSE application manual AM10. There's a flow diagram to determine whether that natural ventilation is an effective strategy or not. Okay, let's look at step number 1 first. In step number 1, the natural ventilation must have an adequate opening. So the opening in 62.1, there's a requirement on the space length, which is determined by the height of the window, or rather the opening side of the window. So in this case, there's a 3 case of opening for a natural ventilation. First, if you look here, this is the opening. You only have one side of opening. Second, you have single side of opening. And third case, you have a corner case of opening. So case number 1, if you have a single side of the opening, so the length in this case A is determined by the height of your ceiling. If your ceiling height is 3 meters in this case, the maximum length that you can declare as natural ventilation is only 6 meters. If your height is 5 meters, the length is 10 meters, 2H more than A. In second case, if your space have 2 opening, which means you are allowed up to 5H to declare that area as natural ventilation. Let's say, for example, your ceiling height is 3 meters, 5 times 3 is 15. 15 meters of the area can be deemed as open as natural ventilation. And third case is the corner opening. So corner opening, it take the diagonal length. Also, the maximum diagonal length in this case is 5H. So if the ceiling height is 3 meters, the diagonal length maximum is 15 meters. Okay, draw it out. Will be easier to understand. 3 type of opening: single opening, double opening, and the corner opening. So single, which means you only have one opening, and this is 2H. H is your ceiling height. Let's say it's 3 meters. So maximum area is 6 meters. Anything beyond 7 meters cannot consider as a natural ventilation. Next case is double. Let's say you have a double opening, and this is 5H. Let's say your ceiling height is 3 meters. Maximum is 15 meters. Anything more than that, more than 15 meters, not considered as natural ventilation. Double opening has a better advantages. So you can up to 5 times your ceiling height. The third case is corner. Corner, you have corner opening. Again, is diagonal is 5H, which means your diagonal is 5 times your height. Let's say your ceiling height is 3 meters, your maximum diagonal is 15 meters. Three case for natural ventilation area. The other requirement is on the opening. So the opening must be at least 4%. So your opening area must be minimum 4% of the floor area. Let's say floor area is 100 meters square. Your opening must be at least 4 meters square. Okay, so opening means your window, your louvers. In this case, we need to calculate the opening size. So for example, in this case, this hospital has 2 sides of opening. You can see there's a window, louvers, and also door. The total length of this building is 7.21. In this case, the height is 3 meters. Floor ceiling height is 3 meters. 5 times 3, 15. So 15 more than 7.21. Okay, in this case, it comply. So window opening in this case, you can see door is quite big and the window is quite big as well. There's a upper, there's an opening, there's a middle part, there's an opening. The opening size is quite big, it's more than 4%. Okay, but for the submission, we must calculate the opening area. Okay, this is a case of not complying. If you can see this waiting area. So this waiting area has the length of 7.5 meter. So assuming the floor height is 3 meter, so maximum allowed for one opening is 6 meter. In this case, it's 7.5 meter. It is not comply. In this case, what we can do, let's say all this room has fresh air duct supplying that area. Okay, we can do some modification by pull the OA duct into some of the area over here. We can deem this area as a mechanical ventilated area supplied by OA, and this area is natural ventilation area. So reducing that 7.5 to maximum 6. Next, have to fill up this natural ventilation compliance form where we key in the zone name, the area, type of the opening, maximum allowed H, like 2H or 5H, and then what's the ceiling height, and what's the distance, maximum distance allowed, depend on the ceiling height. On the right hand side, the ventilation opening provided, how big is the opening provided, what's the actual distance from the opening. So at the end, whether it's comply or not, this need to be filled up for the submission. That's on the first step on the meeting natural ventilation requirement. Next step is to determine whether it is an effective strategy based on the AM10. In terms of AM10 flow chart, we can see here, this is actually the flow chart. But if we look at this flow chart, the final part is this natural ventilation. We need to go through few of the processes to determine whether that area can we go for natural ventilation. First step is, are the maximum heat gain more than 30 to 40 watts per meter square? So we need to fill up a form as well to determine what is the heat gain on all this area. The heat gain can come from window, come from peoples, come from equipment. If yes, it is not more than that, so going down, does the building has a narrow plan? So before that, usually if our heat gain is more than that, it's highly unlikely we can reduce that. If we look at the worst case first, we cannot reduce the heat gain. Next, we looking at is occupancy transient, which means people in, people out, rather than they are staying there. If that area is not transient, we look at whether the capacity can affect absorb swing in temperature and IEQ. In this case, most likely hospital, we can inform LEED that the capacity affect absorb swing. Yes, I mean most of the occupant can accept the IEQ or the temperature. Or if the occupancy is not transient, we can look at is seasonal mixed mode acceptable. Seasonal mixed mode means if winter time or a heating or the summer time, but in our case we do not have seasonal. If we look at this, we can inform that it is able to absorb the swing in terms of temperature and IEQ in that area. So in this case, we go back again. Does the building has a narrow plan? So narrow plan in this case is 15 meter. If the building structure less than 15 meters, we can continue on. Are the noise and pollution level acceptable? In this case, we need to measure the noise level of the area. We can do a sample measurement. And next, can occupant adapt condition and weather changes? Some talk about the thermal comfort of the people, whether there's air movement, additional air movement, fan, the occupant can wear less clothes, okay, some other or the variable affect thermal comfort. And if yes, the occupant can adapt to the condition, also weather changes, then which lead us to the path of natural ventilation. What's important in explaining this flow chart to LEED is, first of all, we already determine the heat gain. If the heat gain is more than that, we couldn't change the heat gain, but the occupancy is transient, or we are able to accept the mixed mood, which means in this case, we only have summertime, we don't have winter or summer. So back to the building again, if the building plan has less than 15-meter width, then we are safe, can go ahead, but have to check noise and pollution level, which means we measure the noise, is if the noise acceptable or not. And then next we go look at the occupant, whether the occupant can accept the weather changes or not. And finally, it leads to the final natural ventilation. So to convince LEED that that area is deemed can be used for natural ventilation, we have to go through all this process. In this case, first we start off with heat gain. We try to calculate what is the heat gain in that area. Of course, heat gain, you can use the 62 point, this is ASHRAE handbook to determine what is the heat gain from the wall, solar radiation, glass, and internal heat load. So that is for the whole IEQ prerequisite requirement for EBOM. Okay, let's go step by step again. Okay, step by step. Step number one, we have to determine the area type, which means either mechanical ventilations or natural ventilations. Okay, that's important. And remember, the area that's served by split unit or served by FCU is at the perimeter with opening, with window. We can use that deemed as natural ventilation area. Okay, that's first one. The next one, we need to know the area, whether it's occupied area or non-occupied area. Okay, so we divide the area into 4 spaces. Next, we determine the area size and the population. That's step number 1. Step number 2, we need the mechanical drawing. So prepare the mechanical drawing, look at the area, look at the system design. And third step, we solve for mechanical ventilation area first. So we look at the OA intake amount. Okay, so by measurement, we can do by measurement or by design. By measurement, we have to follow the audit guideline. We have to measure the input. Remember, there's a 3 type of system, single zone, 100% OA, and also the multiple zone. So important is the OA intake, whether OA intake through a primary ASU or OA intake through a opening. We need to measure that. That's important. Next, we need to fill up the calculator for mechanical ventilated area. Okay, step number 4. Step number 5, for natural ventilation area, we need to fill up the natural ventilation area compliance form. So step number 6, if got natural ventilation area that cannot meet the natural ventilation requirement, whether it exceed the area, okay, so we must do some modification, which means by pulling in OA down, or we put in new ASU to serve OA into that area. Okay, that's number 6. Number 7, natural ventilation area. We have to calculate heat gain for the area. Step number 8, we prepare the following document for the submission. So drawing, if can, mark out MV or NV, mechanical ventilated area or natural ventilated area. Or we divide into Excel also can. Okay. Next, standard operating procedure for mechanical engineering demonstrate that HVAC system could do maintenance program based on 62.1. And we need PM, preventive maintenance work as well, to demonstrate that the PM has been done. And the other document we need is sample of I-beam report, and the last one will be sample of ACMV work order. So with all these steps, then we can prove to LEED that the project was comply to this requirement. With that, thank you very much.